Welcome back, everyone, and today we're going to start continuing our new mini-series about spring physics and get movement and doing fun stuff with springs and spring equations. The last video was a long video where I did a lot of explaining all these different algorithms I found of dealing with springs, and and just basic positioning and moving things around just through just velocity and dampening and spring constants, all this fun stuff. Since that video, I actually learned about two new spring algorithms, and I just want to quickly go through them. They're kind of the same, but they're slightly different. They do break the mold, and it's kind of important because apparently one of them is actually used in physics engines because it's very optimized and very. It's ideally because it has the least amount of operations. Compared to all the other ones, and it's considered to be more stable and more easier to fine-tune when you start combining springs to make like funky hair or clothing or things like that. So supposedly it's supposed to be like if there's like a spring equation to use, this is the one to use. So we're going to quickly go through it really quick, and then we'll start dealing with springs with rotation. So I found this new type of springs from Alan Chow. And he goes really through some of the math behind it, and I kind of don't explain some of it. It's actually kind of confusing, some of the things, because he calls them zeta and omegas and everything else. And but overall, it's the same kind of thing. It's just an oscillation that decays over time. And this article is actually based off of this document from Aaron Cattell, which is looks like he's just like a well-known physics engine developer. I can't remember the article, but he worked for some big game companies, and he's also the developer of Box 2D. And he mentions that I think when he was building a physics engine, he actually learned about these springs from a different physics engine, and he learned how it works. And he says this is amazing, and it actually works really well. And for the physics engine that he writes, that's what he uses because it's pretty much the most efficient. Even though it's unstable, as he calls it, unstable, because the springs can explode. But he says the values you have to throw into one of the equations is unrealistic, and how are you going to use it? You'll never put in that kind of value. So it's unstable, but not in production. Like you'd be insane to use values that high or those specific types of values. As long as you just keep it within a certain range, the equation is supposed to work very, very well. And I've been using it lately for prototyping, and it actually works pretty well. A little confusing how it works a little bit, but overall it's actually fairly pretty good. I still have problems tuning it, but I think all spring equations is difficult to tune, no matter how more efficient they are. I guess this one's just probably slightly better than other ones, but it does perform quite well, and I actually do like certain things about it. So I don't want to spend too much on it. So for completion's sake, I actually fixed up the spring position from the last video, and I just want to quickly look at the equation, or two equations actually. They're actually two different types. I totally forgot to look up what certain things mean. Like there's one. This one's called it's called implicit Euler. It's supposed to be some kind of math term. I keep forgetting to look it up what it actually means. It's like some type of mathematical thing. And overall, this is the equation for performing the springs. Now, this system works a little bit different. There is no there's a dampening. In all honesty, the dampening values are the same dampening values from the previous, like just the regular spring equations. The only difference is there's no spring constant. It replaces spring constant with oscillation per second. So, and basically everything is and you can actually calculate dampening in a certain way that both articles actually mention how to really put it together, which is kind of neat if you want to try to control it or make it like user friendly, or like designer friendly. Just like, you fill in these numbers in, and hopefully you'll have an idea. Even though I'd still have problems tuning it, even based on those ideas. So that the main takeaway is, instead of spring constant, we're gonna have oscillations per second. So basically, how many times are, like, it's like a sine wave, how many times are we going to oscillate back and forth per second? And a complete oscillation, like a complete cycle or a complete period, is 360 degrees, which is pi 2. So like right here, I say pi times 2 times 1. That means for every second, I want to perform one complete cycle. And actually, when playing around with this, it actually works to go under sometimes. Like instead of saying times 1, I say times 0.5. So instead of oscillating at 360 degrees per second, I only oscillate 180 degrees per second. So I slow down the oscillation to give me some nice, easier spring movements, like the ones I was getting from the original spring constant equations. So you do have a damp value. Now, both articles, or I think just one article, calls that damp ratio, and it makes sense to call it damp ratio when you take in consideration these two values. But you really don't need these two values, in all honesty, because damp ratio has to be between the values of 0 and 1. So it's kind of like how dampening is supposed to work in the spring equations. You're supposed to put a value between 0 and 1, but because of delta time, things get screwy, so you have to put like higher values. But this equation works with delta time really well, so you can actually keep the dampening value between 0 and 1. If you put a value of 0 in damping ratio, you would actually get non-stop oscillation. There would be no springing. It would basically be a sine wave, essentially. If you put a ratio of 1, you make it a critical spring, a critical dampening. So that means there's no springs. You will actually speed up and then slow down at the very end. Perfect. So this equation actually does give you much better fine control of the dampening. Now, this equation, like I said, you don't need this equation. Like, as long as you have a slider and just go back and forth, you're good to go. But if you want to kind of like control the dampening, there's an equation here that allows you to say how much dampening you want and how much time it takes to make that dampening. So the idea is like you have a sine wave that's happening a certain amount per second, and then you have a certain amount of dampening around a certain amount of time. So ideally, you're supposed to make the spring movement kind of predictable. I think that's another property of this, because everything is based on time. So if I know I'm doing a 0.1 dampening, but it takes a half a second to do 0.1 dampening, so that means, let's say if I do a dampening, I don't want to really change it, but if I want to do a dampening of 0.5, so I want to dampen by half. So if the oscillation is like going, let's say like a magnitude of 1, after about half a second of time, if I was a dampening of 0.5, that means the magnitude of 1 after 1 second would drop down to a magnitude of 0.5, half. If I spend another second of time that goes by, or I guess in this point another half second, that will be cut in half. So instead of being 0.5, it'll be 0.25. So the idea is that you can actually make the oscillation predictable based on time by using these equations. So you have this equation which allows you to control dampening based on time. Like I said, if you want that kind of level of control, but that equation basically would just give you a value between 0 and 1. So you have two choices: just a slider back and forth, or you can use these equations to kind of fine tune it if you need that kind of predictable movement. So that's why I kind of like this equation, because I like this aspect that you have two things. And like I said, the dampening ratio works really well. Like I said, 0 complete no dampening at all, and 1 gives you critical dampening. It just gives you a nice slow. And I haven't tried going over 1, but then it gives you over dampening, and everything kind of speeds up to the spring, so you get more springiness out of it, I believe, because that's what over dampening usually does. So that's a really cool example. So this is the explicit Euler equation. This is supposed to be very stable. That means you can throw any numbers you want in there, and it'll actually function just fine. Now, there's an alternative to this one, which is called the semi-implicit Euler, and it works the exact same way. You can put in a dampening, and a time. And this one, like there's an example from one of the articles that says just put 0.5 and then your dampening time, and you basically do, I forget it's called like a half-life. So that means for every amount of dampening time, whatever the oscillation is gets cut in half. Just half. And it just keeps dividing the oscillation in half for every amount of dampening time. If you don't want to choose a dampening value, 0.5 can be a good one, and then you can kind of control it just based on dampening time and oscillation per second. So if you want to do it, either one will work for either equation. Like I said, both the equations are practically the same, except like where this one is this big complicated mess, this one is super simple. It's very, very small. I think it's probably just as small, if not smaller, than regular spring equation. So that's why this is the one that's used by physics engines to mimic spring movements. And the original article of the guy who writes Box 2D, he actually calls this soft constraints, not springs. He gives this thing a completely different type of name. So he considers it like a constraint of some kind. But it is a spring. It does move in a spring kind of way. And like I said, but this one's considered unstable because springs can explode. They can just not work predictably. But if I remember correctly, like the only big major thing is like if you don't use like I think if the dampening is negative, I think things become an issue. I can't remember. The one thing I do remember is that if you try to do pi 360 degrees or like pi 2 times 10, then it's going to explode basically. But that's 10 oscillations per second. So that means I even tried when doing 10%. It's insane. It just basically up down. There's no actual movement between top and bottom. It's like it's so fast that you can't see it. And that's the article is right. Even though it's unstable, you will actually never use these values in there because it just wouldn't work for actual animation. So that's why this one's been picked, because the amount of operations is very simple. It's just a bunch of multiplications and a single subtraction. There's some addition here, and you can optimize a couple of things. You can make oscillation per second squared. You can cast that or save that somewhere. You can save this as well. Like cache that value, so this way you have 2 less multiplications you have to deal with. The only deal is that you have delta time in 2 places, so we can't cache too much of the values because of that one deal. And to impose is always going to change for every time you call this function. So you can improve. You can optimize it by removing 2 multiplications and then caching the values to even optimize a little bit further. I don't know how much performance you'll really get from taking away 2 multiplications, but that's one thing to consider. So you can make this a little bit more optimized. But again, these 2 equations function the same way. You have a moving position, and you compare it to a position you're trying to get to, and you have to save the velocity. So it still works like a spring physics equations, like those standard ones. It's just more optimized and easier to use. So that's what like the just. This is it. Like for all the springs that we're moving forward, I'm probably going to use the semi-implicit Euler. So that's the deal. This is going to be included into the source files for this lesson. So for completion's sake, so this way you have the spring pose that has all the 1D equations for springs as a reference. So this way you have them all. If you're really interested in these type of equations, they'll be there. So how do you use this for? So we use it for 1D, right? So, and I think in the end of the video, I showed you how we use it for 3D movement, and it's just like curves. You repeat the equation for every component of your function. So let's see. This is implicit, so let's go to semi-implicit. So this is like basically the vector version of it. It's like I cache certain values. Then I just apply it for every component. You have X, Y, Z. And then, again, I just do the other part, X, Y, Z. And that's all it really is. And guess what? For a rotation, it's the exact same thing for X, Y, Z, X, Y, Z, and W. And that's really how you apply springs to quaternions for rotation. You just do it this way, just like a regular vector. The only thing you have to remember is you have to normalize the rotation value. If you don't normalize it, you will have some weird artifacts, and things will skew. Some things will just not rotate correctly. Especially if you're dealing with like a mesh of vertices, you're moving around, the mesh will start exploding a little bit. It's not a beautiful sight when you don't normalize these quaternion values correctly. So that's the only thing you got to keep in mind. You treat it just like any kind of vector, just normalize it. And that's really the gist of doing spring rotations. It really is. It's just the same thing. Like I said, it's the same thing as doing movement. You just do it in a rotation aspect. So, we can quickly look at some examples. I have all the other springy equations. Like if you want to test them out, like I said, it's not really worth it. Because like I said, it's all the same thing. It all looks the same. So let's go there. So if I go to rotation. And you see, and this is basically it. You're just using that spring equation on all 4 components, and you normalize it. And every time I do a spacebar, it just rotates. And I can just keep pressing spacebar, and it'll just keep on going. It'll accelerate, decelerate where it needs to go, and it just springs itself into its resting position. And that's it. It's just like movement. Rotation and movement is the same thing, and that's it. That's the magic of it. As long as you have a good equation and you set it up correctly for your vectors, and you remember to to normalize it, that's the important key. If you don't normalize it, it won't actually work correctly. And there you go. And you have springy rotations. All you basically, like I said, it works the same thing, the same way as all the other ones. You have a velocity, and you just do it as a vector of velocity, just a vector 4. And you just keep track of that velocity. And you just pass in your target rotation that you're trying to get to. You pass in the rotation you're currently at, and you pass in your velocity of rotation. I wouldn't call it, I don't know what I'll call this, like angular velocity or at all. I don't know if this counts. But like I said, it's just consider it numeric velocity. There's a mathematical term. I keep forgetting what's there's like a weird mathematical term when we're dealing just with just adding numbers up together. It's not displacement. I forget. Someday I'll remember it. Again, I'm not a mathematician. I'm just a self-taught learner. So I can't go too crazy with it. But yeah, like I said, it's pretty easy. So let's say I want to make it more springy. I just increase the oscillations per second. Actually, yeah, I think it takes more. It springs more. I can't remember. Let me try. Let's go for broke. Let's go to the maximum that we're allowed to go. Oh, you know what? It's probably not refreshing itself. Got developer tools open. I wish you didn't need that. Like you need developer tools open to right click and get empty cache and reload. It's just more springy, I guess. And let's make damping time only 1 second. Refresh. Don't notice much of a difference. Am I modifying the right file? Fine. Let's go for broke. You know what? Let's make dampening. This amount of dampening takes about like 3 seconds. Oh wow, something. I don't know if I'm modifying the right file. Or I just keep putting the right values in there. You know what? 0.5. Oh, I'm modifying implicit, but I'm using semi-implicit. Duh. All right. Let's see. Let's go. Like I said, let's just go for broke. 10%. So yeah, it springs. It's so you, like I said, you. Ooh, it's a little unstable at 10. So there's the unstableness. So maybe 10 is not the right number. Maybe you should reach the under 10. Let's try it one more time. Yeah, there you go. So it's kind of like a nice quick boing. So 10 is the bad number. That's you have to be under 10. So I think you could probably do 0.9 and still be good. Let's see if I don't smash the rotation. And good, 9.9. So 10 just can't reach 10. Just it's unstable again. So all right, let's try one more time. Let's try 9.5. Let's just have fun with this. And it's good. All right, 9.5. 9.5 works again. Good. It's not unstable. All right, 9. Oh, never mind. I started talking. All right, so I guess stay at 9. On top of that, I'm actually not stopping the spring at all because I'm not actually like I just the way it's working right now, it just keeps on going. Ideally, I should keep checking to see that how much time I have left. Like, let's say I need to do like a dot product between the rotation target and the rotation of the target rotation and the current rotation. If the dot product is under like 0.0001, and then check the velocity. If velocity is also like near 0, that means I'm at the end of the spring movement, and it means I should really stop animating it. Just make it the target thing, and just set some kind of a flag and stop animating. So this way you're not constantly doing this math. So that would probably help a lot more. That maybe a lot of this unstableness is the fact that I keep springing at these really, really small values, at like, very small values close to 0. So that's probably really what's going on here. But at 0.9, it looks like it's there's a little bit. Nah, it stops. So yeah, okay. So it's stable, but like I said, it might be that reason. Let's just go for funsies. Let's decrease that. Oh. So you gotta play with it. Again, if I bring this down to just 2, and then it becomes a lot more stable. And ideally, this is really the type of spring you're going to be using. So, like I said, implicit tends to be it was considered unstable. But again, you're not going to do that. You're not going to, if you play around with your dampening, you might be able to keep everything nice and stable and get the exact type of spring you want. If this is what physics engines use, so be it. So there you go. So that's what we have. How much time is this? 23 minutes. All right. So we're almost done. So the only thing left to do is that rotating a square is boring. So again, like in this series, we're going to be building up our baller. So here's our baller from Fortnite, and as you can see, the ball has movement. It has a spring movement built in. So now the next thing I put in there is the spring rotation, and the spring rotation you can control it with IJKL. I can't use WASD because I have that mapped to the camera. So I use that to control the camera, so I had to use a different set of numbers. But here you go. I have the cannon that's on the ball. It is just a rotation anyway, so I just do that. I just keep changing the rotation, and I believe I keep track of polar coordinates. So the idea of this one is I just use polar coordinates to determine the rotation, and I just keep rotating. So I defined like the longitude and latitude, and I kind of like when I stop, it just gives that nice spring. So there you go. And like I said, this is a nice practical thing for rotation, like especially since the way it works. It's like it's supposed to be this roller thing on a ball. So if you want to stop on a dime, it's not going to stop exactly on a dime unless you do kind of like a critical. You can do like a critical dampening type of thing to it, so this way it slows down. But I like that little bounce because it to me feels more realistic. Because if you're playing if you're fighting, you know it's gonna be more hectic, right? So it's gonna have that little bounce, and I don't know. To me, it feels like more fun that way. I don't know. Just to be sure, I'm pretty sure. So it's the gun. I'm moving the gun, and so yeah, I have aim X and aim Y. So I'm definitely using polar coordinates to control the rotation, and I have aim. Keyboard move controller, keyboard cannon controller. So, yes. So I'm just using polar coordinates. Am I? No. I'm actually just using Euler X and Y rotation. I thought I was using polar coordinates. My bad. So I'm just creating rotations of X and Y. That's it. So polar coordinates are almost the same, but yeah, I guess I don't know. I've been using polar coordinates for other things, so I thought I was using it for this. But no, this is just regular X and Y Euler rotations. So I just save the value, and during the input, I just increase or decrease the rotation based on which direction I want to go to. So and that becomes my main target. So that becomes the target. So that my target, I start off with that, then I multiply it by the gun's bind pose. So the bind pose is the starting pose of the bone. So it's kind of always basically I'm always recalculating the new rotation, then adding it to 0. If you want, if that's the thought of it, like let's say you're calculating a new origin, and you know your origin, like it's like x of 1 and y of 1. So every time you do math, you always have to do it based on that origin. So this is basically the same idea. I'm doing all this rotation. I'm saving the x and y rotation, and then I just apply it to the origin, like the starting point. So everything keeps nice and smooth instead of just constantly adding on to a rotation. I noticed that causes problems, and it makes things a little bit unstable and doesn't move and predictable. But if you do rotations where you kind of start off at always the exact same point and then just add up all the rotations. Like I said, for this example, I like to say if I'm constantly rotating, I'm just saving the X rotation. So if I'm at like 30 degrees, and then I just added another 10 degrees, now it's 40 degrees. So I say take the starting point and rotate it by 40 degrees. And then the next iteration, I do another 10 degrees. So I say take the starting point and rotate that by 50 degrees. And that makes rotation very stable, especially with quaternions when you're animating. So that's like the simple, easy way to deal with it. Instead of just saying, here's my current rotation and just rotate it by 10 degrees. It doesn't act right. It's not very predictable, and it like doesn't look right when it happens. So there we go. That is it. So that is rotation on springs on rotation. So we got movement and we got rotations. So in the next video, we're going to cover applying rotations on bones. So this way we can create something called a jiggle bone or dynamic bone, but it's something that allows us to make things like tentacles, tails, or the starting point of making tentacles and tails. It also allows us to start controlling hair, making hair movement like jiggle, boob physics, yes, and clothing, and so this way we can start having dynamic animations, procedural animation based on movement. So if I'm moving something, everything will sway based on the movement. So you'll see I already have everything ready. I'm actually going to record it tonight, and it's pretty cool. I put a lot of visualization into it, so to make it easier to make people understand what's going on. So yeah, so hope you enjoyed it. GitHub will have the main 2 files. Spring pose and spring rotation as the examples to learn if you want to play with it. But on my Patreon site, we'll have the baller, because again, I said I don't want to pollute the GitHub repository with these large files. So it would just be easier just to put them somewhere else if people really care about the baller. Yeah, so the baller is going to be with us for a while. We're gonna be using it for a lot as a prototype to keep building and adding on to the ballers. So like right now we added movement. Now we added the control of the gun. And the next one we're gonna control the chair and make that spring itself based on movement. It looks really neat. I can't wait to show you guys in the next video. So, okay, so I'll see you guys in the next video. I hope you have fun. Please like and subscribe. It helps me, even though I don't get anything out of this YouTube thing. I just do it for fun. I hope you guys enjoyed learning it. I don't want to make these too long. The last video was like over an hour. So let me just cut it off. See you guys in the next video. The next one's going to be fun. It's going to be bones. We're going to deal with bones. Oh, yeah. All right. See you guys in the next video.